Hi, my name is Ron Pressler, and I'm the technical lead for Project Loom. Project Loom's primary goal is to make it easier to write high-throughput concurrent applications like servers. But I assume that by now, most of you have heard of it and at least know its main elements. If not, there are quite a few introductory talks you can find online. So what I want to do today is focus on certain areas and certain questions that come up over and over. I or someone else from the project are now online answering questions through Zoom's Q&A feature, so feel free to ask questions at any time. The first thing, perhaps the most important thing to understand about Loom, is why it exists and how exactly it helps. I said that Loom aims to make it easier to write high-throughput concurrent applications like servers. So first, let's see what we mean by concurrency. Oftentimes, concurrency is confused with parallelism. And the distinction between the two is crucial to understanding Loom because it seeks to help with one, concurrency, while other Java features help with parallelism. The definitions of parallelism and concurrency I'm using are in line with the computer science teaching guidelines of the ACM. Parallelism is the problem of speeding up the execution of a single task by splitting it into multiple pieces that are then worked on by cooperating subtasks running on different processing units. In Java, the main feature that addresses parallelism is parallel streams. Or if you want to go lower level than that, then splitrator, which as its name suggests, splits up work, and the fork join pool. Project Loom, on the other hand, addresses concurrency, which is the problem of scheduling many mostly independent tasks that compete over resources. A prime example of that is a server that needs to serve many requests that arrive at a fast rate. And because handling each request takes up a bit of time, they end up concurrently competing over the server's resources. The metric we wish to optimize when concurrency is concerned is throughput, or how many transactions we can serve per second. Because the more transactions we can serve in one machine, the fewer machines we need. The throughput, transactions per second, in a system that serves requests concurrently is governed by this formula called Little's Law. It says that if the system is stable, meaning requests don't pile up in an ever-growing queue, the level of concurrency, or the number of transactions we'll be serving concurrently, is equal to the rate at which requests arrive, which is the same as the rate at which they're completed, or our throughput, or else the system won't be stable, times the latency, which is the average duration it takes to serve a single request. For example, if requests arrive at an average rate of 1,000 per second, and so we must complete them at the same rate for the server to be stable, and each transaction takes 10 milliseconds, or 1/100th of a second, then our level of concurrency, or the average number of transactions we'll have to be handling at any one time, is 10. Now, I've called W the total latency because there's a nuance here worth paying attention to. Suppose that to serve a request, our server needs to contact two services over the network, each responding within 5 milliseconds. If those services are independent, instead of calling them one at a time, taking 10 milliseconds in total, we call them in parallel. We've reduced the latency by a factor of 2, but because we want to do those operations concurrently, we've also multiplied our level of concurrency by 2, and the two cancel each other out. So W is the overall latency of serving a request as if it were done sequentially. So in this case, it will still be considered 10 milliseconds rather than 5. For the system to be stable, again, the throughput must equal the rate of request arrival, lambda. Now, lambda is a requirement of the system. To meet the requirements, we can either reduce W or increase L. Now, W, the total latency, is also usually a constant for any given system, as it depends on how much work we need to do, the speed of our database, etc. So we don't have that much control over it. The variable we can control is L, or more easily control, our level of concurrency, or the number of transactions the system can process at any given time. We can increase it by buying more machines, but that costs money. We'd like to buy as few machines as possible, so we'd like the level of concurrency for any single server to be high. What factors affect L on a single server? There are hardware limitations like RAM and processing cores and network card bandwidth, but there are also software infrastructure limitations that might cause us to make inefficient use of the available hardware, reducing the level of concurrency.